The last two colligative properties that we're going to talk about are boiling point elevation and freezing point depression. So let's start with boiling point elevation. Boiling point elevation. So how does this work? So if we have a beaker of water and these water molecules, like we have covered in a bunch of the other videos, want to start evaporating. And again, this is a pure solvent. We will see some water molecules start to evaporate and make some gas, and then some will start to condense. Equilibrium will be established, and we will have an equilibrium vapor pressure for water, right? Now, what happens when we add the solute? We add solute, and we see this beaker, which was once just pure solvent, now have the solvent and solute. And like I mentioned in the previous video, the vapor pressure lowering effect will cause less water molecules to form above this liquid layer. So the vapor pressure is going to go down. These solute particles will make it more difficult for liquid water to escape, evaporate into that gas layer. So we will see a lower vapor pressure, right? So how does this affect the boiling point? So if we are at room temperature here in both situations, we can see that at the same temperature, the equilibrium vapor pressure is going to be lower for the case with the solute in it, right? The beaker with the solute in it is going to have a lower vapor pressure no matter what temperature we're at. Remember, boiling is when you get the equilibrium vapor pressure to equal the atmospheric pressure. So let's remember that the atmospheric pressure is the air around us. It's going to be always around us in any case that we are in. And the atmospheric pressure is 1 atmosphere. So once the equilibrium vapor pressure gets to 1 atmosphere, you have now equalized the equilibrium vapor pressure, that water vapor, with the atmospheric pressure, the air around us. That is when boiling will occur. So it's going to be the same over here. So, however, we said that at every temperature with a solute, the equilibrium vapor pressure is lower because it is harder to escape. So as we approach 100 degrees Celsius, water's boiling point, right? We're going to see, obviously, as this heating up is occurring, the equilibrium vapor pressure keeps going up and up and up, and eventually you will get to equal out. This will be 1 atmosphere, and you will boil. Now, what happens as you approach 100 degrees? As you approach 100 degrees from 25, you'll start to see more gas. But at 100 degrees, like we said, at every temperature, we're going to have a lower equilibrium vapor pressure. So at 100 degrees Celsius, we have not got to 1 atmosphere yet. This is not 1 atmosphere yet. We need to continue to heat this up past 100 degrees Celsius. I don't know, maybe this isn't real numbers, but maybe we have to get to 120 degrees Celsius before we can get enough vapor in here to equal 1 atmosphere, which will equal the atmospheric pressure. Then it will boil. So just as a summary, boiling is when you equal your equilibrium vapor pressure to your atmospheric pressure. And when you add a solute, the vapor pressure is always decreased. So you need to increase the temperature higher than a normal value than you're used to get that equalized pressure of the equilibrium vapor pressure and the atmospheric pressure. So that is boiling point elevation.